Okay, thank you. This is joint work with my collaborators Nicole Morlita and Brendan Lucier, who are both at Microsoft Research. So I'm going to talk about something a little bit different than what we've been hearing about. The main problem that I'm going to talk about today is we have manufacturers in this world, and they produce great things that we need, like steel or cement. We use them. But when they produce pollution, like carbon. And this is not great for the world. We know we have things like climate change, and so we're trying to reduce our emissions. So what's currently being done in practice is we have something called cap and trade, and what cap and trade does is it says, let's cap the total amount of carbon pollution for the next year. Let's say this is how many tons of carbon can be emitted, and that's it. And anybody who emits carbon in the process of manufacturing needs to hold a license for every ton of carbon that they emit, okay? Otherwise, I'm gonna just give you some severe fine, and therefore your utility is gonna be like negative infinity, and so you don't wanna not hold a license, otherwise it's just gonna be really bad, okay? So you better have a license if you're gonna manufacture something that produces carbon into the environment. So this is what cap and trade is.
This is an international treaty? Or?
This is the system called cap and trade. Not everyone is using it, but this is a system called cap and trade, okay? And so what are our goals in using cap and trade? So why do we let people produce at all instead of just cutting off production if carbon pollution is bad for the world? Well, obviously there's also economic value in production. We like cement, we like steel, okay? So we're trying to trade something off here, is that we like the economic value of these things, but we don't want too much carbon in the world. Okay, so our goal is going to be to trade off the economic value from these manufacturers with the societal cost of the pollution. There might be other goals that we have as well, such as reducing the emissions, distributing the licenses efficiently so that we get the right manufacturers producing, since we only have a limited amount of production, or encouraging clean technology. We have certain technology right now, it pollutes carbon, but maybe there's other technology that we could develop that pollutes less carbon, and maybe there's a way to get these manufacturers to develop that technology, and because they're internalizing the cost by having to have these licenses, our mechanism could cause them to develop this technology, okay? So these are some of the nice things that we could do by using market regulations, okay? So the question that I have left on the table is, how are these licenses allocated? We know there's a fixed number of licenses that we're capping, and everybody needs to be holding one, but who gets the licenses? And that's the mechanism that we need to design, okay? That's the problem that we're gonna talk about today. Okay, so emission trading schemes, who's using them? Is it an international treaty? No, definitely not. The first emissions trading scheme was developed in 1995. The biggest one in the world today is the European Union Emissions Trading Scheme, which raises tens of billions of dollars every year. In America, where I'm from, we basically don't use them. There's a small one on the East Coast in New England and New York called RGGI, the Rhode Island Greenhouse Gas Initiative. It's very small and it's not working very well at all. There's the Western Climate Initiative, which is California and most of Canada. There's the Korean Emissions Trading Scheme. There's one in Australia and New Zealand. There's many around the world. The main one is the European Union one, okay? They all do something a little bit differently, but almost all of them use a very similar mechanism to distribute the licenses. This mechanism is the uniform price auction. Okay, this is what's being used in practice today in most of the emissions trading schemes. So what is the uniform price auction, a refresher? It goes as follows. The government sets some cap C, okay? In our example, let's say the cap is 5. It's just a toy example. Obviously, the real cap is much bigger. Then the firms are going to submit some decreasing bids. So for example, the Blue Factory says, for the first license, I'm willing to pay $45. For the second license, I'm willing to pay $35. For the third license, I'm willing to pay $25. Okay, and so on. They're non-increasing. Then we're going to allocate to the C highest bids. Okay, so what are the 5 highest here? First we have $45, then $40, then $35, then $32, then $30. Those are the 5 highest ones. So that's who's winning here. Right now I'm assuming that they're just truthfully reporting their bids, okay? So that's who wins in the uniform price auction. And then what's the payment? Well, I'm going to use a uniform first price auction. So we're going to charge the C highest bid, the lowest winning bid for every license, okay? So the price is $30 because that's the lowest winning bid. So what does that mean? That means that the blue factory here is getting 2 licenses because he has 2 bids that are in the winning bids, and he pays $30 for each of them. So totally he gets 2 licenses and pays $60. Cool? Okay. Now, just to recap, sometimes we use the uniform second price auction, which is the highest losing bid, but what's being used in practice is the first price auction. So that's what I'll focus on today. Okay. Now, because there's uncertainty in practice and we don't always know exactly what the manufacturer's valuations are, there are a couple of modifications used on the auctions in practice to try and get around this uncertainty. What these are a reserve price, or a price floor, and a price ceiling. And this is how they work. The reserve price says, let's never sell below some price floor, P lower, okay? I wanna make sure that I'm never selling too low. And so if I set a price floor of $33, that means that I'll never sell to anyone who bids below $33. So in this example, it means that I won't sell to the bids of 32 or 30, okay? I'll only sell to the top 3. And then my price, instead of being $30, that's not going to bind. Instead, I'll just sell at the price floor, the reserve price of $33. Does that make sense? Okay. So one of 2 things is going to happen. Either the cap will bind, I'll give out all 5 of the licenses that I'm supposed to, and then we'll use the lowest winning bid, or we'll hit the reserve price, in which case we'll charge the reserve price for everyone. Just want to make this point now. The other thing I have is the price ceiling, which says that you can always buy extra licenses at some P upper. So this is going to be some really, really high P upper, like $100. And it's just to say, in case I get the demand totally wrong, you can always buy extra licenses at $100.
That's basically the same as imposing a fine,
Right. It's basically the same as imposing a fine. Yeah. It's basically the same as saying the fine is $100 if you don't comply. Sure. Yeah. Okay. So this is the uniform price auction with the 2 extra parameters, and this is what's being used in practice. Any questions? Great. Okay, so what's the problem? The problem is that the uniform price auction is not truthful. Okay, let's see why. Let's say in an example that the government sets a cap of 3, and we have the following bids. Blue says $45 and $35. This is our best allocation for 3 licenses, is we have the top 3. And let's say that the cost to the government is $30 per unit. This is how much there is of an externality of polluting carbon, okay? So what is welfare? Welfare is just the economic value minus societal cost. And so in this example, where we have 3 licenses, it's just 45 plus 35 plus 32 is the economic value here, minus the societal cost is 30 times 3, okay? And that's $22. Now, what is Blue's value for this allocation? Well, the lowest winning bid is $32, so the price per license is going to be $32, which means that Blue's utility is going to be 80, which is 45 plus 35, minus 2 times the price of 32 for both licenses is $16. Great. Yeah, was there a question? Blue is the left one. Sorry, yeah, Blue is the left factory. Okay, what if Blue instead reports the following bids? What if Blue instead says, I only want 1 license for $45. Let's pretend I don't want the second license. Here's what happens. The 3 licenses get distributed differently. The price now drops by a lot. The price drops down to 10. Blue does only get 1 license, so that's less than before. But Blue's utility goes all the way up to 35. So the color might not be showing up great, but Blue is getting $45 for the first license, but the price is now down to 10, so Blue's utility has gone up to $35 instead of the 16 it was before. What's more is if we look at the welfare for this allocation, the welfare of this allocation, so I just want to point out this is a beneficial deviation, and the welfare of this allocation is $87 for these 3 licenses minus the same societal cost, which is negative $3. So the problem here is it's negative. And the reason we're getting something negative is because of this mixed sign objective of the economic value minus the social cost. Why is something negative bad? Well, if we go to approximation and we're trying to approximate something positive with something negative, we're not going to be able to do that. Okay? So that's the issue here.
If the cost is 30, then why didn't you put a price floor first?
Good point, Ben. Thank you. I didn't plan him. So this is actually an easy case where you can just set a price floor of 30 and it makes everything simple. But if we have different social costs, it's not necessarily so easy. Okay, so this is an example where it would be easy. So the point is that we have a problem of demand reduction, where bidders will want to reduce their bids in order to get lower prices.
But even if you did set a reserve of 30, then blue could still lower 35 to 30 if you was.
Yeah,
That's what they said.
no, that's not what I said, but I agree, I agree with you.
That's true. That's a good point, yes. Okay. True. But it does prevent this allocation. But it does prevent the negative welfare issue. It doesn't prevent the demand reduction entirely, but it does prevent the negative welfare. Okay. So the question is, how do we deal with the fact that the uniform price auction is not truthful? Okay. So let me tell you what our goal for this work is. Yes?
You're assuming that it's not complete information game? That is one factory knows exactly...
No. Okay. So the benchmark that we're going to try and target is the expected welfare of the welfare optimal uniform price auction, assuming truthful reporting. So this is what's happening in practice. They're using uniform price auction, and they believe that they're getting truthful reporting. Okay? Why? They either aren't considering strategic issues, or they believe that there's perfect competition, that all of the firms are small enough that there should be perfect competition. However, in practice, there are actually emissions trading schemes where there are firms that have a large enough market share that there should not be perfect competition. So we should expect to see some strategic behavior, okay? So our goal is to set parameters for the mechanism used in place. We're not going to try and design something entirely new. If we wanted to, we could just use VCG and everything would be dandy, but we're not going to. This is the mechanism used in place all over the world, and we just want to say, since you're using it all over the world, how should you tune your parameters to give guarantees, okay? So how can we set the parameters for the uniform price auction such that in any Bayes-Nash equilibrium, so this answers your question, in Bayes-Nash equilibrium, so you know the prior distributions, which we'll get into the model in a second, the welfare is a constant approximation to the benchmark, okay? Again, the benchmark is assuming truthful reporting for the best uniform price auction. And so this is going to be a price of anarchy type of result, because it's for any Bayes-Nash equilibrium. So our results are that we do this by 1, we assume independent bidders, and 2, we have a no dominant bidder assumption, but you'll see that it's not an assumption necessarily. And also, I want to note now that price ceilings aren't necessary, so I said that was one of the parameters. What we prove is that you don't actually need price ceilings. It's quite easy to approximate a mechanism with price ceilings without them, so I'm just going to drop talking about price ceilings for the rest of the talk. And we also have other approximations with differing assumptions in case you don't like these assumptions, okay? But I won't focus on them today, okay? So let me touch on the related work. Was there a question? No? Okay. So here's the related work, which I'll just skim through. There's a bunch of work on carbon taxes, cap and trade, and in general, your emissions trading schemes, but they all focus on non-strategic markets, okay, where there's perfect competition, which again, I'm arguing that we need to focus on imperfect competition because there are markets where there are large enough firms that this is an issue. The second thing is there's much work in demand reduction and uniform price auction and what to do about it, but these assume that there are no costs. There's no societal cost or production cost, okay? And since we have that, we need to worry about it. Third, there is work on auctions with production costs, but these are largely impossibility results, negative results, and we want some sort of positive approximation result. So in order to combine all 3 of these to deal with cap and trade and carbon tax with societal costs, when we're in a strategic setting, then, and get a positive result, we need to do something new, okay? Okay, so here's a model, which I'm gonna explain entirely in pictures, so I recommend you look at the slides. So here's our societal cost. It's going to be a convex green curve, okay? This is the cost of society when we pollute in the number of licenses. So the more licenses we give out, the worse it is for society, okay? In terms of pollution. There are going to be N agents and manufacturers. Each of them has a valuation, and it's going to be marginally decreasing. It's privately known what their valuation is. Only to the red firm does the red firm know what their valuation is, but it's drawn from an independent distribution, and everybody knows what the distribution is, okay? So assume that we have some data and we know what is it going to look like in general, but not exactly what their valuation is going to be. We don't know exactly what the economy will look like in the future year. Okay, so here, for example, is what the blue firm and the yellow firm and the red firm's valuation curves might look like. Now, these are the cumulative valuations over the number of licenses. So if we want to back out what is their valuation for each successive license, it looks like for the first license, Red's value is $40. For the second license, Red's value is $30 because Red's value for 2 licenses is $70. Okay, and so we could then take Red's bids to be $40 and $30 and so on. Does the picture make sense? Okay. Good. So our goal is to maximize expected welfare. The way we want to do this is we can draw some sort of combined curve that says, first we give some of the licenses to the red firm, and then to the blue firm, and then to the yellow firm. Why are we doing it in this order? Well, from the last picture, what I showed you is that this is the cumulative curve of how much multiple licenses are worth to them, and therefore the slope is how much each license is worth to them. So we want to allocate to the steepest slope first. This is the highest value per license. So red has the highest value per license, and then blue, and then yellow, and then blue again. And we're trying to maximize economic value minus societal cost, so that's the biggest gap between this cumulative curve and the societal cost curve. Does that make sense? Okay. Now, one of the things is that this is strategic, so this is the ideal allocation, but it could actually be bad. This is only if we are actually able to figure out who to allocate to. So it could be bad as this least efficient curve, right? If we can't figure out who to allocate to. And so what in between are we achieving? How can we get our mechanism to try and get closer to the optimal thing? And the second thing is I said maximize expected welfare. We don't know exactly what these curves are going to look like. They're going to be drawn from some distribution. And so we might have several different realizations depending what they are. And so how do we optimize the expected welfare depending on what the draws of these valuation curves are? Okay? We might have very different ops depending on the draws. Does that make sense? Okay. So the uniform price auction is parameterized by some cap and reserve price, as we talked about, since we're forgetting price ceilings. And so I want to show you what these curves look like when they're parameterized by these parameters. Okay? So here's a valuation curve. You should think of this as the multicolored curve that I just drew, but I'm going to just draw it as a blue curve from now on. Okay? So this is actually all of the players together, and this is the ideal curve if we can just allocate efficiently. So what's happening here is this is the point where the price floor, the reserve price, binds. This is the point where there is a bidder who is not willing to pay the reserve price, okay? So up until this point, all of the bids are at least the reserve price. Here it's equal to the reserve price. Here it's tangent. So this means in the uniform price auction, I'm stopping allocating and everybody is just paying the reserve price. This is like what we showed on the first slide about the uniform price auction. If instead the curve looks like this, then all of the bids are steeper or greater than the reserve price, and therefore the cap is binding. So I'm allocating all of the licenses up to the cap. Okay? So either of these two things can happen, but we're not going to get opt for each realization because we can either have the reserve price bind or the cap bind. Only one of these two things can happen for each curve. And since opt for each curve can look like this point here, we can't simultaneously get an opt for each realization. Okay? So what can we do? We're not trying to get opt for each curve. We're just trying to get the best uniform price auction under truth telling. That was our benchmark. Okay, I want to reference some previous literature which says that even though the uniform price auction is not truthful, without costs, we know that the Bayesian price of anarchy is at most 3.15. So what does it mean? It means that for this curve, we know that even under worst case strategic behavior, we can always get at least 1 over 3.15 fraction. Okay, it's at most here when it binds at the cap. And so this is just the non-strategic, the truth-telling reporting over the worst strategic behavior, okay, of the mechanism. But what happens is once we introduce the societal costs, it can become negative. So here is, again, the truthful reporting, but now if we have costs, this can be negative, and so when we have this fraction, it can be unbounded. And this is, again, because of the mixed sign objective. So what do we do now? How can we deal with the fact that this is unbounded if we want to get an approximation result? So our idea is to set what we call a safe price floor, and what we do is we peg this reserve price to our societal cost curve at the cap, okay? Why do we do this? And I claim that this gives back the 3.15 price of anarchy result. And I'm gonna show you in an informal proof by picture. Of course, you can do it formally by math, but I'll show it in an informal proof by picture. Okay. So I wanna say that the bidders, the people who make up this blue curve in the picture on the left, have the same utility in the picture on the left as they do in the picture on the right, okay? If the same bidders here. Why? In the picture on the left, they're paying this is the price they're paying, is the red curve. This is the price they're paying, and this is the societal cost curve, okay? So in the picture on the left, each bidder is at the blue point and they're paying the red point. So their utility is the blue point minus the red point, okay? And that is the same as paying the blue point minus the red point in this picture. So they're getting the same utility. And so in this picture on the right where there's no cost curve, we have the old price of anarchy result. So we know we're at the 3.15 here. And if we translate that back to here, we get 3.15 up here. We can just translate it upwards, rotate it upwards, and then we get a 3.15 above the societal cost curve. And now we get a 3.15 Bayesian price of anarchy above the societal cost curve, where it's not a mixed sign. Does that make sense? So you just rotate, you have the same utility, and then you can just rotate it upwards and add in the costs. Yeah?
After you change those curves, don't you get weird properties like decreasing with the number of licenses or something like that? Like here, it can decrease when you get more licenses.
Here, what decreases?
The curve can go down.
Don't have to expose it.
Doesn't it hurt the original group or something like that?
What? I didn't understand what's going down.
The blue curve is supposed to be non-decreasing.
Negative steepness.
It's, okay, yeah, good point. No, it's okay, yeah. No. No, it's a good point. It's not a problem in the proof, yeah. Yeah. Okay, so the question is, since we get our price of anarchy result back, we know that we have these nice strategic properties. Since we have our nice strategic properties, can we now use them to approximate the benchmark? So we know there's good strategic properties, but we don't know whether, since we're now working with a small class where you have to use a specific price floor, a specific reserve price, can it approximate it's a much smaller class, and can it approximate when we can set any price floor and any cap, okay? So that's the question that's left. Unfortunately, the answer is no. And it's an example which I don't think I really have time to get into, but basically the bidder has high variance, and if you were to set the cap and the safe price, you can only capture any single realization that the bidder has, and you would not get the welfare from any other realization at a time. So that's the problem, but it's just a single bidder with high variance. And so instead, what we find out is that if you either have a single bidder and you treat the single bidder specially, then you can do okay, or you can use a safe price auction if you don't have a single dominant bidder, okay? So if you have a single bidder, then you can do something like using VCG to have a contract with just the single dominant bidder and everything's okay. Or if there's no single dominant bidder and everybody's independent, then what you can do is carve up the space, which I'll show a picture of but not get into. We also have, and this gives a constant factor approximation. We have some other results that don't necessarily require independence, but this is our main result. This is what carving up the space looks like. Essentially, you can say who is hitting the price floor, who's above the cap, who's below the cap, can we set a different cap, what's optimal, et cetera, and uses some nice concentration inequalities. Okay, so just let's recap. There was some strategic behavior of demand reduction, and the price of anarchy was unbounded. So what we did was we set a safe price floor, and it limited the strategic behavior. And then by either treating just the single bidder by itself, or by having no dominant bidder and independent bidders, then we could get an approximation. There's a lot more to do in this line of work. We just focused on the efficiency of the initial allocation, but there's much more going on in these emissions trading schemes. There is the effect of the auction on technology investment, which I hinted at in the beginning. There is the secondary market, which is pretty crazy. There's the fact that you can bank your current licenses for future years. You can borrow licenses from future years. So you can say, I don't have a license now, but I'll buy it in the future. You can say, okay, I think the prices are going to become very expensive in the future, so I'll buy more licenses now and hoard them for the future. You can trade in the secondary market. There's much more analysis to be done here. There's the fact that they're not actually sold just once a year, they're sold 4 times a year, so there's repeated sales here. I think there's a lot more for algorithmic mechanism designers to study here. I wanted to say a little bit about the fact that most of mechanism design touches on revenue maximization with a couple of social good applications, and that I think there's a lot of room for more domains and using tools from revenue maximization, from gains from trade and welfare maximization to try and get into specific domains. I myself am trained in revenue maximization originally, but I am now trying to use these tools in other domains. And I think that we can come up with interesting questions in theoretical mechanism design from these domains and also give back potential solutions. And I'm not going to preach anymore. Okay. Thanks. Yeah.
So my question is, I'm trying to translate this back into the theory world where I feel safer. Is it just equivalent to having a multi-unit auction where the seller has its own increasing values for the items?
Yes. Exactly, increasing production cost, yeah. Do you feel safe now?
Yeah.
But yeah, so what makes this different? Let me clarify. Okay, so the question was, does this just translate back into multi-unit auction where the seller has a production cost that's increasing? And the answer is yes. What makes this different than some of the work that's been done is that I am really focusing on this uniform price auction with the specific parameters, and the motivation for that is because of what's being used in practice and tuning the parameters for that. Yeah.
You could have said simplicity, but...
Yeah, Avi.
Do you not care who gets the allocation at the end? Like if there's a monopoly on pollution or something like that, is that a problem?
That is not something we focus on. There's no fairness work here in terms of like maximum fairness or anything. Yeah. Did you have a question? No.
Okay.
Thank you.